Now for a short presentation on reaction types. The first reaction type I'd like to talk to you about today is the combustion. In a combustion reaction, we have a fuel that reacts with oxygen. In the case of this course, we're going to be studying hydrocarbon fuels, such as methane, reacting with oxygen to form CO2 and H2O, or perhaps propane, C3H8, reacting with oxygen to form CO2 and H2O, or butane, C4H10, reacting with oxygen to form CO2 and H2O. There are many, many more examples, but they all work the same way. Balancing these is kind of interesting. The best strategy is to leave oxygen for the very last. So let's look at the first example. In the original reactant, we have one carbon. There's one carbon in the products. Carbon's fine. Hydrogens on the left, there are 4, so I need 2 waters. And now I count the oxygens, 2 here and 2. Now that I have 2 waters, it makes 4 oxygens, and so I need to put a 2 in front of the O2. Then the equation is balanced. In the second example, 3 carbons requires 3 CO2s. 8 hydrogens requires 4 H2Os. We'll count the oxygens. 6 here, 4 there, make 10. I need 5 pairs, and that equation is balanced. C4H10, there are 4 carbons, so I'll put a 4. There are 10 hydrogens, so I'll put a 5. And now I will count the oxygens. 8 and 5 makes 13. Now I have a little bit of a problem because these O2s are in pairs. They come in pairs. I can't get 13 out of pairs. So the strategy here is to go back to remove the coefficients we put in earlier and go back and double the original fuel. If I do that, I now have 8 carbons, so I'll put 8 CO2s. 10 times 2 is 20 hydrogens, so I need 10 waters. And we'll recount the oxygens now. 8 times 2 is 16, plus 10 is 26. I need 13 oxygens, and this one is balanced. So if you end up with an odd number of oxygens on this side, go back and double the original fuel and start it again. It will be fine. The second reaction type I'll talk about now is decomposition. This is when a single compound in the reactant side decomposes and makes 2 or more products. Good examples of this would be water decomposing to form hydrogen and oxygen. Hydrogen peroxide reacting decomposes all by itself into water and oxygen. KClO3, potassium chlorate, when heated, decomposes and produces KCl and oxygen. Let's see, salt can be electrolyzed, electrically decomposed to form sodium and chlorine. Those are some simple examples. I can also have something like H2CO3, carbonic acid, decompose into water and CO2. These are all possible decompositions. Let's go back and balance them. In the first one, the oxygens are uneven. I'll do that to fix the oxygen. And now I double the hydrogen, and I have a balanced equation. In the second one, seems that I'm kind of in trouble with oxygens here, but I'm not really sure what strategy to take. So I'm going to try the old give it a shot, throw a 2 in there and see what happens. Let's see what happened. 2H2 means I need 2 waters. Now let's count the oxygens. 2 times 2 on this side is 4. right here, and I have 2 here and 2 here. The equation is now balanced. The third one, I have 3 oxygens on the left and only 2 on the right, so I'll use a least common multiple approach. Now I have 6 oxygens on both sides, and I'll fix the KCl. This next example, my problem is the chlorine, so I do that and fix the chlorine, and then I double the sodium, and we're all set. And the last one, if I count carefully, is already balanced. So there you go. The next type of equation we'll talk about for a few minutes is combination or synthesis. This is when we have 2 or more elements or compounds and they make a single product. An example of this would be hydrogen and oxygen making water, or let's see, calcium oxide and CO2 making CaCO3, or perhaps, let's see, aluminum and bromine making AlBr3. In each case, we can go back and balance the equation. In the first one, we need to fix the oxygens first and then fix the hydrogens, so we're all set. The second equation is already balanced. And the third equation, I have an odd-even bromine thing going on here, so I'll double this one for 6 bromines on the product side, triple this for 6 bromines on the reactant side, and then 2 of those, and we're all set. This next kind of reaction is the double replacement, in which 2 ionic compounds in aqueous solution react with one another to form 2 different ionic compounds. However, since we're dealing with positives and negatives, there's really only one possible way that the new products can form. And so we use this ABCD example, and you can see that A and D go together because they're plus and minus, and C and B go together. Simple example of this would be something like potassium chloride reacting with silver nitrate. This would form potassium nitrate and silver chloride. Notice potassium's +1, chloride's -1, silver's +1, nitrate's -1, so that when we put them together, they automatically have the right plus-minus combinations, and so we end up with neutrally charged, correctly written formulas. I can do this again with something like, for instance, NaOH reacting with, let's say, CaNO3, 2. In this case, sodium's +1, hydroxide's -1. Calcium is now +2, nitrate's -1. When they switch, the Na, which is +1, goes with the nitrate, which is -1, so that's a correctly written formula. And the Ca, which is +2, combines with hydroxide, which is -1, requiring parentheses and a 2. This is not balanced until we go back and put a 2 on the sodium hydroxide and a 2 on the sodium nitrate. One more example. Let's go with Na3PO4, combination of +1 sodium ions and -3 phosphate ions, and then barium chloride. Barium is +2, chloride is -1. When these combine, the Na, which is +1, will go with the chloride -1, so that formula is already written correctly. And the Ba, which is +2, will go with the PO4, which is -3. Now I need to get a little fancy here. I need 2 phosphates and 3 bariums. So I've kind of got a big old messy complicated formula over there in the products, but that's okay. We balance by putting a 3 here, a 2 here, and a 6 on the NaCl. The final reaction type for today is single replacement, in which an element reacts with a compound, forming a different element and a different compound. Good example is one that you've probably seen in class, where zinc metal reacts with hydrochloric acid to form hydrogen gas and zinc chloride. We used that the time that we generated hydrogen gas and then tested it with a burning splint to make the little whoop sound. Let's balance this. Need to put a 2 here, and then we're all set. Another example of this would be something such as, let's see, aluminum reacting with silver nitrate to form silver and aluminum nitrate. Now, aluminum nitrate has this formula because aluminum is +3 with nitrate, whereas silver is only +1 with nitrate. So in order to balance this, I need 3 here and 3 here, and then we're good. You notice that in this case, we have an element and a compound forming a new element and a new compound. Once you are secure in what's going on in this chapter, you should be able to do the following. You should be able to recognize, hold on. Once you're done studying for this chapter, you should be able to both recognize and balance equations of the 5 types. So all 5 types. You should also be able to write some fairly simple equations from words. You will find practice problems for this in the quiz found at the end of section 11.1. This test coming up on chapter 11 also includes a few mole conversions, which you'll remember from before. Let's go on and do one quick page of mole conversions, and then we'll call it quits. What you see here should look familiar. This is our little diagram of how to do whatever mole conversions you might need to do. So let's try a quick example. If I had 1.80 grams of carbon and I wanted to turn that to moles, we would set up a conversion factor in which 1 mole of carbon was in the numerator and 12.0 grams of carbon was in the denominator. We would then divide on our calculator. First, we can prove that we're canceling correctly, and then take out your calculator and divide 1.8 by 12, and you will get, let's see what we will get. You will get 0.150 moles of carbon. If we had a number in grams, such as, let's say, 800 grams of NaOH, and I wanted to turn that to moles, I would have to say that there's 1 mole of NaOH in the numerator divided by a molar mass of 40 grams, and so that again cancels correctly, and I will get an answer of 20.0 moles of NaOH. Let's try one where we start with moles. Let's say I started with 2.50 moles of water, and we wanted to turn that to grams. My conversion factor now has 1 mole on the denominator and the molar mass of water, 18.0 grams, in the numerator. We are canceling moles. And let's see, 2.5 times 18 is 45.0 grams of H2O. So in this case, we're using the molar mass. If I had 1.50 moles of neon and I wanted to know how many atoms that was, I would put 1 mole on the denominator, 6.02 times 10 to the 23rd atoms in the numerator, And I would then take out my calculator and multiply. Moles is canceling. And my answer is going to be 9.03 times 10 to the 23rd atoms. Good luck. Study hard. Notice that we have quizzes. Ooh, what's that? Let's make that go away. We have quizzes at the end of each reading section. And in this chapter, you can focus on 11.1 and 11.2. Please omit 11.3. We did not cover some of that information. There is also the study guide answer key posted on the portal on the Chapter 11 topics page. Have fun. You can do well on this test. I know you can.